now we're going to be moving into Chapter 8, which focuses on hypothesis testing. You need to know that hypothesis testing is another type of statistical inference. We studied confidence intervals back in Chapter 7, where we used a sample to make an assertion about the population. We used a statistic to make an assertion about the parameter. We're going to do the same thing here, just with a different method, and that's with hypothesis testing. And there are 4 steps that we're going to go through for hypothesis testing. We'll look at 2 steps in this video and then 2 steps in the next video. The first step for a hypothesis test for just one proportion, one percentage, is going to be to form a pair of hypotheses. The null hypothesis is our HO or H naught. This is HO or H naught. And it assumes the proportion P is equal to a value. So the null HO will always be in the form P equals some value. We have some baseline that we can use from experience or from a previous study. The null is always assumed to be true until the end of the hypothesis test. It's like in a court of law, you're innocent until proven guilty. We're assuming the null is true until we can prove otherwise. In addition to the null, the other option is the alternative hypothesis, the HA. This assumes, based off of some new information, some change, some difference, that the proportion is now not equal to, greater than, or less than the original value from the null hypothesis. It'll be the form HA, and then P is either not equal to, slash greater than, slash less than that original value from up here. And we're going to use statistics to decide which route we take. Do we support the null hypothesis or do we reject the null hypothesis? And our statistics will tell that. After you have your hypotheses, then step 2 is to check the central limit theorem. And we saw this back in Chapter 7. The central limit theorem, the CLT. This allows us to use the properties of the normal curve, that bell-shaped unimodal distribution. Just like before, we need to make sure it is a random sample and not a convenient sample or a voluntary response sample, but it's random. And we need a large enough sample size. Our expected successes are n times p, and our expected failures, n times 1 minus p, are both greater than or equal to 10. That's still the magic number. So for an example to walk through these first 2 steps, it says suppose that flipping a coin high in the air yields equal probabilities for heads and tails. However, suppose that spinning a coin makes tails more likely because the head side protrudes more than the tail side. So instead of flipping the coin high into the air, it's like we're spinning it on a table. It says suppose the coin is spun 100 times and it comes up tails 64 times. If I wanted to walk through a hypothesis test to see if tails is more likely than heads, my first 2 steps would be as follows. Step 1, I would give my HO and my HA, my null hypothesis and my alternative hypothesis. HO always has the form P equals some value. The population proportion is equal to some value. And in this case, it's going to be 0.50. From previous experience, from flipping coins, we know we have equal probabilities for heads and tails. It's a 50-50 chance you get heads and tails. My alternative is going to be that P is greater than 0.50. It says suppose spinning a coin makes tails more likely. So it's not a 50% chance you get tails, but it's somewhere greater than 50. Maybe it's a 60-40 split or a 70-30 split. We don't know what it is, but we think it might be somewhere greater than 50-50. I would walk through some statistical steps and I would decide, well, is the null ultimately true? Or does our sample cause us to reject this and say it's somewhere greater than 0.50? Before I can get to those statistical steps, I need to go to step 2 and check my central limit theorem. I need to check 2 components. Number 1, my sample type, and then number 2, my expected successes and failures. So in this case, can I say that I have a random sample? If I read the problem carefully, the word random doesn't appear once. But the act of spinning a coin 100 times, that is a random act. You can't spin this coin and have control over the coin and make it land on heads every single time, or make it land on tails every single time. There is an element of randomness when you are flipping a coin or spinning a coin or rolling dice or spinning dice. Then, for my expected successes, I'm going to take n my sample size times p. N is 100 times. Times p, we said in the HO was 0.50. That gives me 50. That's over 10, so it is met. As well, if I try to find my expected failures, n times 1 minus p is also going to be 50. They're both over 10, so it is met. Now, I know these 2 numbers always add to be the sample size. And so because the sample size was 100, I know 50 and 50 add to be 100. Just a quick note before we move on. My actual success number is 64. And my actual failure number is 36. It came up tails 64 times. That's my success number, which means it came up heads, the other option, the failure, 36 times. So my actual results aren't looking like it's 50-50, but it's like a 64-36 split. That's not enough to say that, yeah, tails is more likely, because this skewed sample could happen by random chance. I need to prove, or not prove, but try to show that this is so rare that it's going to change my idea about the HO. And we'll begin to look at how we can do that in the next video.